Today we are going to talk about Materialized View, User-Defined Functions, Aggregates, the new JSON syntax, and the new FullText Search index that had just arrived 1 month earlier. So, Materialized View. Why do we need Materialized View? Until now, I used to tell people, okay, if you want to query your data into Cassandra by different axes, you need to denormalize. What it means is, for example, I have a user table. The user ID is the primary key, so I can query my user by ID. If I want to find my user by country, I need to create another table, user by country, where the country now belongs to the primary key, so I can query on it. But manual denormalization is very boring because you need to take care of the update yourself as a developer. So we solve this problem with Materialized View. Okay. So this is the syntax. I want to create a view called user by country as a select of country ID, first name and last name. So you can decide to copy all of the columns from the original table or just some columns from the base table user where country is not null and ID is not null. Why? Because you cannot have null value for primary key, of course. And then you define the new primary key for your view, okay, which is country and ID. So in fact, Cassandra will create this table in the background for you automatically. And Cassandra will take care of the update. For example, if I create a new user with, I don't know, a new Russian user, Cassandra will insert a new record into this table with Russia as country. If I update a user country from Russia to USA because he moved to USA, Cassandra will remove the Russian record and create a new record with USA as the country. Okay, so the update is done automatically for you by Cassandra. About the performance, of course there is no magic. When you are writing to a table which has some attached materialized view, the write is slower because every time you insert a new record into the base table, Cassandra will block the current row to read the existing value and then to update all the views. Okay, but the cost is paid only once. If you have 1, 2 or 3 views, you only pay the cost only once. Okay, and for each update, so each mutation to the cluster, Cassandra will create extra mutation for each view. Okay, so in worst case you will have 1 extra delete and 1 extra insert for each view. Now, if you want to compare the performance against the case where you have to denormalize manually, it is better because when you are using views, the update is done inside the cluster. It doesn't go back to the client. Okay, so you are saving some network traffic and it makes your life easier as a developer. What about the performance of Materialized View compared to index? Because for example, people, they used to create secondary index to be able to search. Okay, with the view, you always have a single read pass. You are reading directly to one partition on disk and 1 machines. If you are using secondary index, you have 2 read paths. 1 to read the index data and 1 to read the original data. So in fact, Materialized View will always be faster. Okay. You are paying the price at the right time. You write extra data so that when you are reading data, it is very fast. About consistency, you know that in Cassandra we have eventual consistency, okay? and you are using consistency level. For example, you are doing a select with consistency level 1, quorum, and so on. So the consistency level is exactly the same for the base table, for the user table, but for all the views, the guarantees are weaker, because when we are inserting in the base table, we are also updating all the views, but asynchronously. So there is no blocking call. And because all the updates are asynchronous, we don't have strong guarantees. Okay. Any questions for the views? Can we do it synchronously? No, because it is a design choice. If you want to update all the views synchronously, imagine you have one table and you have 3 views. So you insert in quorum. It means that you are writing 2 replica out of 3. And if you are using quorum and you have 3 views, it means that for each view you are also writing 2 data. Okay, so it's like 2 plus 3 times 2. It's like you are waiting for 8 right on the cluster. It is very, very, very expensive. It is too expensive, in fact. So it is a design choice to make all the updates asynchronous. In this case, if you are ready to pay for a price, you should use the classical de-normalization when you are writing, you are updating yourself your own de-normalized table. All the question? Clear? User-defined function. What is it? The idea is to push the computation directly on the server. Okay, so if you are having like 10 machines in production, there is no much gain. But if you have a lot of machines in production, for example, Netflix, they have 1,000 machines in a cluster. Okay, so when you are pushing computation to the server side, you are saving some network bandwidth. Okay, and also it can accelerate pre-aggregation for Spark. So let's see how to create an user-defined functions. This is a syntax: create or replace function if not exists, the key space name, the function name. Here you have the parameters name and the type. The types are Cassandra types, of course. Okay, text, UID, big integer, and so on. Call on null inputs. It means that in your source code you have to check for null values. Returns null on null inputs. It means that if any parameter has a null value, Cassandra will not execute this function and will return null directly. So you are sure that you will never have null pointer exception. Okay. Return type. Well, you can define the type of the return data. So it can be any Cassandra type, a primitive value, a collection, list, set, and map, tuple, or user-defined types. Then you decide which language you want to use for your function. So by default it is Java. You can use JavaScript, but it is slower. You can use Scala and so on, but you have to add extra dependency on the server library. And then you put the source code here. But you know, defining just a function is very easy, but it's not that useful. What is useful is to define aggregates. Okay, how can I compute the sum, the average, and so on directly on the cluster? I don't have to fetch all the data on my server to compute the aggregation. So to create an aggregate, this is the syntax: create or replace aggregate if not exist. The aggregate name. This time you specify only the types and not the parameter names. Then you have to specify a function, accumulator function. It is like a reduce function. Okay? If you are familiar with Java 8 stream, you have the reduce. Okay, so it is very similar to a reduce function. and you need to specify a state type. So you have a state to accumulate your data, and you need to define its state and its initial condition. There is a trick here. Your accumulator function, your reduce function, signature should be something like this. So the first type, the first argument type should be the state type of the aggregate. And then all the remaining types should have the same types as the aggregate. Okay? And the return type is also the state type. So in fact, your function is taking an existing state, apply some computation, and return the new state. Okay. Reduce function. Finally, you can apply a final step to your aggregate. You should be careful with user-defined aggregate in Cassandra. This is the aggregation is not distributed on the cluster. So the computation is not done by each replica. First, Cassandra will fetch all the data from different replica to the coordinator node, and then it will compute the aggregation on the coordinator node. The reason is because Cassandra needs to resolve all the consistency issue with last breakpoint, with the timestamp. Do not execute aggregates on a large partition because it will be very slow. And also increase client-side timeout. If you know that you are going to compute an aggregate on, I don't know, 10 millions or 100 millions of rows, of course, it will take time, okay? It will not answer in 10 milliseconds, of course. So you should increase the timeout on the client side. People ask me, should I use Cassandra user-defined aggregate or Spark? Apache Spark for analytics, for aggregation. Well, the answer is very simple. If you are aggregating in a single partition, use Cassandra UDA. If you want to aggregate on multiple partitions, Spark is better for you. Because with Apache Spark, the computation is distributed. Any question? Yes.
Which Java version is supported in this function and aggregation, and also how can I use third-party libraries in these functions?
Okay. Which Java version? User-defined aggregate are already there in Cassandra 2.2, so Java 7, but it is also there in Java Cassandra 3, so you can use Java 8 with Cassandra 3 and Java 7 with Cassandra 2.2. Sorry, it is decided by the server. If you want to use Scala or Groovy for your user-defined function or aggregates, you have to install extra jar in the server. There is no magic. By default, we support Java and JavaScript because in Java 8 you have the Nashorn JavaScript engine. But it is not recommended because it is slow. Okay. Using JavaScript in JVM is slower than native Java, of course.
So, another questions? Please raise your hands. Who wants free beer tickets, maybe? You can ask questions. Anyone? Okay.
User-defined function shared class loader with main Cassandra instance or isolated?
Aha, excellent question. I have some slide for you. Extra UDF. Extra. I know that some people are going to ask. So, compilation, execution. In a separated thread pool, so you don't impact the thread of the native Cassandra server. And I think also that we have separated class loader also. Fine. Oh, he's happy, so I'm happy.
Okay, anyone else? Because we have time.
Oh,
I
don't.
think-
Oh, wait. I have a lot to talk. So
Yeah, you can continue maybe about share your experience, how to work and how to contribute.
JSON syntax.
Okay.
Why? Why should we use JSON? JSON is a very good exchange format, but it is a terrible schema. And you don't have schema with JSON anyway. You can put in anything. So the idea here is use Cassandra schema. We have a schema full database. You have create table, but then you can query Cassandra, and then Cassandra will return the result as a JSON. And you can expose the result on a REST interface. Okay. So how? I create a user table, insert into user JSON. So instead of defining all the columns, insert into user ID, age, state, and then values, blah blah blah, you just push the JSON text directly to Cassandra, and Cassandra will try to match each column with the correct type. Or you can use the classical syntax, values, and then you have an user-defined function from JSON. So you convert a text from JSON to the correct type. Update also, you can use the from JSON function for update or for delete. Okay. And for the select, you have the same things. Select JSON star, so it will return you just one column which contains the JSON payload. Okay. Or you can just compose select JSON age state or to JSON. So let's see some example. So I have my table JSON user. So I created something complicated with some collection, so you can see how it works. So I have a list of hobbies. Okay, each user has some hobbies. I truncate my table. I insert to user. Okay, John Doe, which has hockey and movies as hobby, and Helen, which has cooking and politics as hobbies. And then I do a select JSON star from JSON user. So here they are. Fine. Now I want to update the hobbies for Helen. So I said update set hobbies equals to from JSON. So instead of passing a list, I am just passing a JSON list. And now it is updated. Okay. So pretty simple. So it is quite flexible. You can choose to convert just some columns to JSON or all columns to JSON. It's up to you. Any question? Yes.
Can you put some more difficult structure? I mean, inner children, like tree, building something like tree.
Oh, you have a tree,
Yep.
a hierarchy.
Yep.
Yes, we can do this with user-defined type. And until now, you can have a nested structure of user-defined types. So there is no limit in terms of depths. The problem is they are frozen. It means that you cannot update them atomically. In the next release of Cassandra, you will be able to update them atomically. So it means that you can have you can store like a document structure with user-defined type, with nested types, nested collection, and you can have JSON syntax. So in fact, you can have a document database, but with a schema.
And when you say that you have some limitation with atomic reading, so does it mean when it's something like cache that have no?
No, for example, you have like a. Imagine that. Let me show you some example. Imagine that here I have a hobby and I have addresses, which is a list of frozen address. Address is a custom type. Okay. The limitation right now is it is frozen. It means that the address, which has some columns, are serialized as a blob and stored in one column. So you cannot update the address. For example, you cannot update the street number. You need to rewrite the complete address.
Okay, I see.
And in the future, you can just say update address dot street number.
Thank you.
Question here.
About previous section, does Cassandra have some mechanism for caching result of function execution for function with the same parameter set?
No, there is no caching.
So if we run my function and put, for example, 100 times this function will be executed.
What you have is the caching of the data itself. You can have key cache or row cache. So the classical caching, so it doesn't depend on the function. For example, you are doing select star from artist limit 100. And if you do the same query 10 times, and if you activate row caching, you will benefit from row caching. So the fact that you use a function or not function, it doesn't matter. What is important is to activate the cache, the row cache.
Okay.
Anyone else?
So let's finish by something great. Size index. Until now, you know, people who are used to Cassandra, they know that searching with Cassandra, and especially FullText search or multi-criteria search, is very difficult. It's not possible with Cassandra. Okay, you have very limited search predicates. You have equalities, inequalities only on clustering column, and you can only search on the columns which belongs to your primary key. You have also already an existing secondary index, but it is very in terms of performance, it is very poor, because in fact it is just a reverse index. Okay, and the index data are stored directly in Cassandra itself in another table, hidden table. Now we have a new index. The idea here is, instead of using Cassandra to store the index itself, the people have created new index structure, suffix trees. Okay, you have extended predicates, equalities, inequality, like. Yes, this one you can now do like percentage in Cassandra. FullText search with tokenization, stop world stemmings. So if you are familiar with Solar Elasticsearch, Apache Cassandra, you know what it means. And also they created a query planner, like in Oracle, right? If you have some complicated predicate, the query planner will build a tree of expression and will optimize all the predicates for you. We don't use Apache Lucene for this new index structure. The reason maybe because we don't want to have an external dependency on a third-party library. Who? It has been developed by some people, engineer from Apple. Those people. Okay. So let's see some demo. FullText search. I have a table which is called albums. So this is an aggregate function. Okay. I have 110,000 albums. So let's see. if I do select star from, no, not star, title, artist, country, year, from music albums, limit 10, just 10 to see how it looks like. Okay, so this is how it looks like. You have some title, you have some artists. Okay, in my database I have all artists in the world, Japanese, so on. United Kingdom. Oh yeah, the artist is a Japanese artist, but the album has been released in UK. Different. Yeah. So on. Okay. I want to create index on those columns. So first, on the title, I want to be able to do full text search on title. Mod contains. What does it mean, contains? Contains, it means that I can use the like percentage. Great. I want also tokenization. Okay, so standard analyzer with stemming. Skip stop words, normalized lowercase, and the local, because when you are using stemming, you need to specify the local, which language. So I choose English. I want to be able to search on artist name for the album. Mod contains, but this time non-tokenizing analyzer. I don't want tokenization. I don't care. I want to search on country using prefix only, and I want to search on album year. Okay, so I created all those indexes. Now let's see. Give me all the albums where title contains Love, released in USA between 1940 and 2010. Okay, so here we are, Love. Where is Clover? Oh, as you see, we have also Clover. Why? Because I just specify percentage. It means that I want all the title which contain the substring Love. So Clover, it match, of course. Now let's see how tokenization work. Love. Okay, just the word love. I should have love or lover. Where is loves also. Why? Because loves and love, they are the same word. Because of we activated stemming, so all the words are reduced to their root. Okay. Now something more interesting: dance and chair. What? Dance and chair in the title? Okay. The chairman dances. Tokenization and stemming. So it means that even if I put dancing, it will work and we return me the same result. Oh, no, not dancing. Dances. Okay. Return me is the same thing. Or chairs. Why dancing doesn't work? Let's see. Dancing. Oh, dancing is different than dancing. Weird. And that's it. So yeah, you can have lots of cool, interesting features with Sassy. When Cassandra 3.5, it already exists in Cassandra 3.4, but it has some bugs, so I debugged it, and all the bugs have been fixed, so you can use it in Cassandra 3.5. Later, they will improve the index to support OR clause. It means that in the future you will be able to query with expression like this, with OR and grouping and so on. and they will introduce also index on collection, set, list, and map. People ask me, how does it compare to Elasticsearch, Solar, and so on? Well, you should know that Cassandra is a database, and this new secondary index is just a feature on top of the database. Cassandra is not a search engine, okay? And using the SASE index, it will be always slower than if you are using Elasticsearch. Why? Because there are two paths. First, you are reading the index data, and then you come back to read the original data. When you are using Elasticsearch or Sora, you are just reading the index itself. Okay? There is no scoring. There is no grouping. There is no group by, and there is no ordering. For example, give me the first 10 results. Okay, but I cannot order by release year or whatever. So if you don't need ordering, grouping, or scoring, this index is fine for you. If you need extra feature, well, search engine. There is no magic. Question?
What languages are supported for full scan search?
What do you mean by full scan search?
This type of index new.
Can you ask again the question?
SI index. What languages supports?
What? Can you ask the question again? I don't understand.
This type of index that you present.
Yes.
What languages it supports?
What language? Oh,
languages. Russian.
Russian. You have a lot of them. You have many main languages like Russian is supported. English, Portuguese, French. So because it is using the library, the Snowball stemma. So.
Okay, so not only English.
Yeah, not only English, for sure. Yes, I have tested with French. I updated the local to French, and yes, it works for French also.
Thank you.
Yes.
Hi. As I know, for Cassandra 2.0 to 2.1, we allowed to filter in about on columns which participate in clustering key or primary key.
Yes.
And what about the FullText Search? Can we use any column of the table to
Yes,
indexing?
you can use any column if you create an index on this column. Title is not a column which belongs to the primary key, but we create an index on it. In fact, it is using the secondary index interface, and the implementation is just different.
What about performance? Does it do some full search on all clusters, or it creates special tables on one?
I have an extra for you also.
Thank you.
Extra, you see. So how does it work on the cluster? It is a distributed search. So it will follow the token range. Okay. So first, give me the first 1,000, I don't know, albums. The coordinator will query the first node by token range. Concurrency factor 1. It returns some data. Do we have enough data? Do I have 1,000? Yes, no. If I don't have enough, start querying more machines. If I don't have enough, start querying more and more and more. So in fact, it is exponential. The idea is I don't want to query all the machines on the cluster, because if I have a cluster of 200 or 300 machines, I don't want to hit everyone. So this algorithm is used.
Okay. Thanks.
Hello.
Hello.
Let's say we have a multinational audience which is searching across the column family. Okay. So, and we are specifying some index for the some specific locale, with some terminators and some stop words. How is it going to work, for example, for Korean people or for English people?
It doesn't
Are we
work.
going to have separate indexes for this?
It doesn't work. In my example, I have like an album table. As you see, they have international languages. There are some Russian, there are some Korean, Chinese, well. And when you choose the local English, it only do the stemming for English. So in your case, if you want to support all the languages with stemming, you have to separate them in different table. Sorry, there is, yeah.
Okay, thanks.
Other question?
Okay.
You told that we can build more difficult indexes like prefix indexes
Yes.
that have like and or syntax. Could you
Yep.
give an example how
Yep.
how it looks like?
The OR is not yet implemented. I said it in the future, but the prefix is working. Like, give me then, something like this. Yeah. No, not title, artist name, because it is
There is no such index.
artist like. Give me some artist name, John. Oh. What? Did I index the artist? Yes. Wait, I just re-indexed. Good question. You destroy my demo. Huh?
I need to.
Yeah, but you are right. Don't trust people. No result. Oh yeah, country USA. Just remove them.
But you told earlier that you prepared all the extra PDF.
Yeah. Okay. So John Adams, Johnny maybe. Oh, where is Johnny? For example, if I remove this, it should give me John also. Yeah, you see? Johan, and so on. Oh, where is my cursor? So yes, it works with prefix. And because I configure my index as title, dance, right? Let's see. No, because I configure the contains, so I cannot do prefix search on this. I should put the double percentage, or I can use suffix search. It means that I can do something like this. Then sing. No result. Oh, lots of result. Yeah. Love. Suffix search. So it depends on the mod contains or prefix.
Okay, thank you.
Welcome.
Hello.
Hello.
Could you please tell us some couple of words how reindexing is implemented?
Re-indexing.
Yeah, on a huge number of writes, for example.
Oh, you asked the right question. Life cycle of SASE. It follows the same life cycle as SS table. So in your insert data, it goes to commit logs, to mem table. It creates an index mem table, radix tree for prefix, concurrent suffix tree for contains. And if you are using all the types and text, for example, numbers or UUID, it uses concurrent skip list set. Now when you flush to disk, SASE will create for each SS table a dedicated index file. So So it follows the same life cycle. It means that if you have compaction, well, also the index file are compacted. If you are doing repair, you are streaming data flush to SS table, it will create the same time the index file. So for one SS table, you have one index file. And of course, it costs you some bandwidth for write because you are writing more data. Okay. And you can rebuild the index like a normal secondary index. It will remove everything and restart building from existing SS table.
Okay, and during the reads, there is some lock on this?
No. So the read is very simple. It will, when you are reading on this index, it will read on index mem table plus index on disk. Exactly like how you are reading on Cassandra data, mem table and on disk. And it will merge the result from two structures.
Thank you.
So we have 3 minutes for questions, maybe. Maybe someone also want to beer ticket.
No.
Okay, I think that's all. Thank you for presentation.
Thank you.